it's not like a real lecture if like, oh, that's true. If it doesn't like at the last minute, no. Oh, perfect. Okay, I'm gonna introduce you, all right? Okay, so hi, I'm Cynthia Chan. I'm a biology teacher and the science department co-chair at Hoover High School. So I would like to thank you all for coming, all the staff and students. Okay, this is a Mr. Robinson word, to this colloquium on the topic of gravitational waves. You can tell I didn't write this. One of our physics teachers, who's also my department co-chair, Mr. Robinson, is supposed to be doing this introduction, but the flu has taken him out of commission. He was particularly excited for this talk because Dr. Chen's work on gravitational waves enabled Mr. Robinson's master's thesis on the same topic. On top of that, one of Dr. Chen's most recent papers, Gravitational Wave Signatures of Nonviolent Non-Locality, references work done by the son of our other physics teacher, Mr. Chagoulian, his son Dr. Chagoulian at UC Santa Cruz. So physics is a small world, okay? At the high school level, we teach students the physics developed between 1687 and 1905. Rarely are high school students exposed to the cutting edge of physics research. We hope to, in a small way, remedy this shortcoming of physics education today. So here is an introduction of Dr. Yanbei Chen. Yanbei Chen was born in Beijing, China in 1977. After receiving a bachelor's degree in physics from Peking University in 1999, he joined CalTech as a graduate student and did research in gravitational physics and quantum physics under Professor Kip Thorne, receiving his Ph.D. in 2003. In 2004, he moved to Potsdam, Germany as a staff scientist at the Max Planck Institute for Gravitational Physics, which is the Albert Einstein Institute. In 2007, he returned to CalTech as an assistant professor and was promoted to full professor in 2013. He was elected a Fellow of American Physical Society in 2015, and as a member of the LIGO Gravitational Discovery Team, Yanbei received the Special Breakthrough Prize in Fundamental Physics in 2016, the Gruber Cosmology Prize in 2016, and the Princess of Asturias Award in 2017. That's a lot.
Yes, our team together won a few
Your
awards.
team together, yeah. So the topic of the talk today is gravitational waves, sounds from the distant universe. In 1915, Albert Einstein invented the general theory of relativity, which describes gravity as an effect of the geometry of space-time. In the 100 years that follow, more and more predictions of general relativity were verified. For example, from the bending of light by stars and galaxies, the deviations of planetary and stellar orbits from Newton's prediction, the slowing of time by gravity, and the way the universe has been expanding. In 2015, the detection of gravitational waves allowed us to measure the bending of space-time caused by colliding black holes, which took place several billion years ago. In the past 10 years, we have detected more than 100 such collision events. So gravitational wave detection has become a fruitful tool for observing the universe and for studying physics of black holes. So in this talk, Dr. Chen will discuss how gravitational wave detectors work and what we can learn from gravitational waves. So let's give a big hand of welcome. Dr. Chen.
Thank you, Ms. Chen. Let me move my computer to the other side very carefully.
Gingerly.
Oh, no. No. I think it's just we need to plug in. Right?
Probably is.
Yeah, I think it's the connection.
It's this one over here.
Oh, is that connection?
Oh.
Okay.
Oh, okay.
I will turn off the light.
I'm so sorry for ruining. Okay. Okay, I think it's working. Okay, great. It's a great pleasure to be here. And it's also very nice to see you. Thank you for coming to my talk. So the topic, the title of my talk is Gravitational Waves, Sounds from the Distant Universe. And I will explain a little bit why I say these are sounds. So I will start introducing gravitational interaction. So people first started realizing the effect of gravity by observing the planets. For example, by the year 1600, already the Kepler's laws were discovered already, and that we have these planets. I think by the 1600s, we only have these inner planets up to Saturn, I think, discovered, that they go around the sun. So these are very different. The planets are very different from stars. So if you look at the stars on the night sky, they follow this pattern of moving from the east to the west every night. And then during the seasons, they have their change of their height and their locations, but they're very regular. And the planets, they look very different in the sky. Like from day to night, the location look a little bit weird. And only if you put the sun at the center, you realize that, oh, these planets, they all go around the sun. And depending on their distance away from the sun, their periods are also different. So Kepler summarized the way these planets move around the sun, but then it was Newton who figured out the way to describe why these planets are going around the sun in this particular way. So Newton did it by formulating his laws of physics. So he has the 3 laws, right? The first law says if things don't feel any force, they will move at constant velocities. And the second law says, well, things accelerate if you have a force acting on them, F equal to ma. And the third law is about action and reaction. And then he formulated his gravity, law of gravity. He says that with objects that are a little bit at a certain distance, depending on their mass, they would have an inverse square law that governs the gravitational attraction force between them. And using this gravity force, it describes the motion of planets going around the sun, in particular that, by the way, he also invented calculus, and he used the tools for calculus to show that these orbits are ellipses, and then the periods of these orbits are related to the semi-major axis, which is like the size of the orbit. And also the same laws of gravity that attracts the planets to the sun is the same reason why the things fall from the apple falls. So therefore, he's able to describe the world in a mathematical way. And that's a very big deal for modern science. Because starting from Newton, he not only realizes that you can use tools of calculus and physics to precisely describe the motions of things, and also he shows that things in the sky, in the universe, follow the same laws of physics as the things on the ground. So it really started modern science. So that's in the 1600s. So basically, after the 1600s, physicists started not only describing gravity, also there are laws of physics that pushed technology forward, and in particular that included electromagnetism. Okay, so from the years 1700 to 1900, scientists formulated the laws of electricity and magnetism, and they developed these elaborate equations that describe how electromagnetic waves move around. And they also show that the light and also radio waves, they are all forms of electromagnetic waves. And they showed that the speed of light in vacuum, okay, that just means that, okay, the speed of light in empty space is 300,000 kilometers per second. And they also showed that this speed of light can be computed from physical equations. And that speed must be the same for all reference frames. Okay, so apart from electromagnetism pushing forward technology, for example, there was the radios. Now people can send signal across the ocean, right? And there were like electricity, all of these technologies. From a fundamental physics point of view, the theory of E and M is very strange, in the sense that if you predict that light has to travel at the same speed regardless of for which reference frame or for different observers, that's very contradictory from the old Newton's point of view. So the idea is if you have a box, and inside the box, you shine some flashlight, and then the light inside the box travels at 300,000 kilometers per second relative to the box. And then, what if you make the box move at 150,000 kilometers per second? Okay, like for us on the ground, then how much will the light move? How fast will the light move? Normally you would say, if I have some car which is driving around and some person in the car running relative to the car, you have to add up the speed, right? But it doesn't work in this case for the light. Normally you would say, I'm gonna add the two velocities. I think if you're learning physics, I think that's what they're teaching you to do, maybe in high school physics. But once the speed is very high, it doesn't work like this anymore. So around the year, like 1900s, people started having experiments. They don't have cars that run super fast, but they can send some fluids moving at some speed, and then they can see the light traveling in the speed and try to measure the speed of light relative to the ground. They have these kind of experiments, and they show that indeed the addition doesn't work. Okay, it turns out and there are other experimental signatures that said, well, the speed of light is 300,000 kilometers per second for every observer, and it doesn't matter how fast the observer is traveling. So this had Albert Einstein established his theory of relativity. Okay, so this started with the special theory of relativity, where his starting point is that the speed of light must be the same for everyone. And in this theory, he started posing this interesting point of view. He said, if space is where things stay at, and the time is how long it has passed, right? Space and time are our coordinates for labeling events in the universe. And he said that, well, if we draw space and time together in a coordinate system, if you have different observers which are traveling at different speeds, their axes of space and time are aligned in this particular way, where you have to think about not everyone share the same time coordinates. And instead, when you have different observers, their space and time coordinates transform in these new ways that he invented in the special theory of relativity. And he and his teacher, Minkowski, they together labeled the theory as having a space-time geometry. So you consider space and time as a same thing, because previously, or our common sense tells us that space is a space, and time is just different. Time is when it is, and space is where. And then we have different words for space and time. But what Einstein said is that you can only reconcile the fact that the speed of light is the same for everyone by considering space and time together. And then, when you consider these together, it's not only this is when and this is where. Depending on the reference frame, the when and where are mixed. Okay, so then the two words are mixed in that way. So the special theory of relativity was able to reconcile a lot of the physics for things that move at very fast speed, including effects that involves electromagnetic waves. So that special theory of relativity had a lot of success, and then Einstein and other physicists started thinking, how do we put gravity into the reconciling gravity with the special relativity? So in particular, in special relativity, light is the thing that is traveling the fastest. nobody can travel faster than speed of light. But Newton's law of gravity previously had no speed, that it's instant. Newton's law of gravity says the force between two guys are 1 over r squared. There's no time in it, okay? So gravity takes no time to propagate for Newton. So Einstein and other people said, well, because of special relativity, because the speed of light is the fastest speed, we have to reconcile gravity with that. And then when people reconcile gravity with relativity, Einstein realized one interesting thing, which is that different objects all fall with the same acceleration. Okay, so this is a very ancient game that I played like 10 years ago. I think for you guys, you probably never played it before. It's one of the apps that iPhone had at the beginning. So it just shows that it doesn't matter what material things are made from. They all fall at the same G, right, G. And Galileo is here because he's the person who allegedly demonstrated it by throwing 2 balls from the Leaning Tower of Pisa. And so people took the this equivalence principle says basically all masses follow the same acceleration. So people took it as an interesting artifact, or yes. Newton also knew it to build his law of gravity, but Einstein took it very seriously. Okay, he said that there's something fundamental about gravity, that every kind of thing falls with the same acceleration. He made it a principle. So it is a equivalence principle, but he made it the foundation of his theory of gravity. So in his theory of gravity, instead of thinking gravity as a force, okay, so before Einstein, people said, well, the big masses, they feel more gravity, their forces are proportional to their mass, but their acceleration is the force divided by the mass. So therefore, you multiply the mass, you divide the mass, and they cancel out, and everybody has the same acceleration, mathematically. But here Einstein says, no, we don't want that. We just want to say that the space-time that he and Minkowski described, having a geometry, but it's a curved geometry. So he has a mathematical theory behind it, saying that basically when things move when there is an object with a mass in space-time, it will somehow make the space-time geometry curved, as if you have some kind of this kind of shaped surface. And when things move on the curve, on this kind of shaped surface, even if they try to move along a straight line, they normally don't move along. They move along the curved line. Okay, it's like if you have a trampoline surface and you have some kind of coin, it'll naturally move with some kind of a curved trajectory. And that trajectory is the straightest line on that trampoline deformed surface. So Einstein developed a whole mathematical theory behind it, which conceptually is very simple, in the sense that then, because it doesn't matter what kind of ingredient you have, they always follow the straightest line that is ever possible. But the mathematical, the conceptual idea is very beautiful, of course the underlying math is very complicated, can be very complicated. But in any case, that is his general theory of relativity that he developed in 1915. So when he applied, okay, so basically the idea is that these straightest possible lines on the surface is called geodesics. It's just like in the surface of, I'll give you an example. Okay, so the idea is that in the solar system, because of the gravity of the sun is it is actually, relatively speaking, not so strong, the deviation of Einstein's theory from Newton's original theory is very small. Therefore, we're able to explain all the planetary motion, most of them using Newton's theory. But there are tiny deviations from this. Let me explain a little bit this curvature, just going into the math of curvature. So this is an apple, okay, so it's allegedly Newton realized that there's gravity by observing the apple falling. So what is curvature? So if you think about it, if you look at this apple, you naturally think, oh, this surface of the apple is curved. So let's see how the curvature can relate to gravity by thinking about having some parallel lines on the surface of this apple. So if you have two parallel lines on a flat surface, they will just be parallel and not approach each other with a constant distance away from each other. It's a parallel. They stay parallel forever. But if you have a curved surface, okay, this is just like on the surface of the Earth. You have the grand circles, the great circles, right? The longitude lines are great circles on the surface of the Earth, right? So basically, you see these two parallel lines, they start out being parallel, but because of the way this apple curves, they approach each other over time. So this is called positive curvature in differential geometry, in math, okay? So then, basically, if you view this in space-time, it means a positive curvature in space-time would show that things move toward each other as if they're being attracted by gravity. So you can also have negative curvature. For example, in this region of the apple, what you find out is that when you have two parallel lines that start out, they will move away from each other gradually. And this region of the apple is said to have a negative curvature. And then you can say, oh, if I have a space-time curvature which is negative, it is as if you can have scenarios where things repel each other. So basically, the tools of this kind of so-called differential geometry, which describe curved surfaces, can be used to describe gravity. Because physics, there's the physical fact that everybody, regardless of their ingredients, they fall along the same line, okay? And therefore, geometry can be used to describe effect of gravity. Okay, so the one way to think about it is that there's a relation between curvature and pi, okay? So what is pi? Pi is the circumference of the circle divided by 2 times the radius. So in the flat space, pi is 3.1415, okay, very, very many digits. So one way to think about it is that there are 3 kinds of curvatures. This kind of a zero curvature, negative curvature, and positive curvature. Depending on the kind of curvature you have, the pi you have here are different, okay? So if you draw a circle on the surface of the Earth, and then you compute the circumference, and then you compute the radius, what you find out is that the circumference is actually less. The circumference is less than 2 pi r, okay? The pi is that pi, okay? So circumference is less than 2 pi r. And also when you draw a small circle, very, very small circle, this, okay, it's hard to see, but the idea is that when you have a small circle, the pi is very close to 3.1415. But if you have a bigger and bigger circle on the surface of the Earth, the circumference divided by 2 times radius becomes smaller and smaller than pi. Okay, and that's the signature of the positive curvature of the Earth. If you have this kind of a saddle point, saddle surface, saddle-shaped surface is as a negative curvature, what you find out is that the circumference over 2 times radius is bigger than our usual pi. So this is a little bit of a connection, give you a little bit of feeling, okay, of curvature. And this basically when you have a gravitating object, when you have some kind of massive object somewhere here, it'll change space-time and it changes the value of pi, in some sense. Okay, so basically after Einstein proposed the theory of relativity, it was mainly thought that these are tiny corrections. For example, in the solar system, you have to measure the motion of Mercury to the very tiny details, and you see that, oh, every century or something, the orbit gets a few arcsecond corrections. It's very tiny corrections. But people do take the predictions of relativity and did conclude a few more extreme predictions. So over the past 100 years, okay, these predictions become more and more observed in actual physics. Okay, so let's start from the first prediction. So the first prediction of relativity is the black hole solution. Okay, so it is a kind of space-time geometry that is resembles the outside of a star, but that star has to be very, very, very compact. Okay, so if you take the sun and if you squeeze the sun to a smaller and smaller and smaller radius, less than a few kilometers and then even less than, let's say, 1 kilometer, then the space-time geometry outside of that matter becomes this so-called black hole geometry, okay? So the feature of this black hole geometry is that this describes the space curvature. So the space is curved around this center, okay? And then this describes the rate of flow of time. So the idea is that around this, let's say, inside this space-time, you not only have a curved space, and then you also have a situation where the flow of time becomes slow and slow and slow, and then the time stops on the horizon of this object. So the idea is that if you take a star and then you try to squeeze it, take the sun, if you squeeze it, when the radius is less than, let's say, 1.5 kilometers, you know, the so-called Schwarzschild radius, when you take it and you further squeeze it, then the star would go into this horizon, okay? And what you have is just a pure empty space with a curved space and with time slowing down on this so-called horizon, okay? And no matter is visible anymore because all the matter are beyond the horizon and they cannot come out. So Oppenheimer is actually the person. Oppenheimer and his student Snyder are the people who gave a mathematical description of how a star would collapse and form this geometry. I think that was before he moved on to work on the atomic bomb. Okay, so the black hole is a very intriguing object. It was first predicted in 1916 of a non-rotating, spherically symmetric around black hole. And then a little bit later, people found other solutions which correspond to rotating black holes. And for example, also light rays can travel around these black holes, which is also a very unusual effect because the light is very fast and normally they will escape from the stars. But from the black holes, they cannot escape from the horizon and they can travel around the black hole at a circular orbit. So people made a lot of imaginations about what a black hole would look like. For example, because gravity is very strong and because light can travel around these black holes, so therefore if you put a black hole in the foreground and then you view the universe in the background, you see this kind of pictures, and then you see a lot of these things which are due to the light rays from the stars bending back and forth around them. So black holes has triggered a lot of imaginations. On the other hand, in astrophysics, in the past, let's say the past 100 years, okay, since black hole, the mass was discovered, astrophysicists discovered black holes from the electromagnetic radiations. So the first kind of discovery of black holes are in these binary star systems. Okay, so these are objects which are seen to emit a lot of X-rays. So X-rays are electromagnetic waves that have very high frequencies. Okay, so they're and the photons they emit are very energetic. They're a lot of energy. So basically, when you want to emit X-rays, you have to have electrons accelerated and then stopped by some kind of target, by some kind of thing, like you have the dental x-rays, okay? Dental x-rays, they have some electron being accelerated, the electrons are stopped, and then they emit x-rays. Or you heat something up to very high temperature, very high temperature. You can't heat it up to the temperature of the sun. It's probably not enough to emit a lot of x-rays. You have to have very high temperature. So these are black holes, and the reason why you can see these x-rays from the black holes is because you have a companion star, and the gas of the star is falling down the black holes. And then when the gas falls down the black holes, they have frictions and they get heated up. And then this is one origin of X-rays in the universe. So this is just an artist picture. So the X-ray telescope detects X-ray photons, and then they do some counts, and then they can make models of these kind of systems. And so these are so-called stellar mass black holes. So these black holes formed because they were pretty heavy stars, and then after they burn out their nuclear materials, they would undergo some explosion and implosion, and they cannot support themselves under their own they cannot resist their own gravity anymore, and then they become black holes. So the other kind of black holes live at the center of the galaxies. So for example, at the center of the Milky Way galaxy, there is a black hole which has 400 million solar masses. So it's 400 million times the mass of the sun. And these are pictures of stars that orbit these central black hole of the galaxy. And then from these orbits, people can measure the mass of these black holes. So these are the kind of black holes that exist in our universe. It's seen that, and also, this is the more recent black hole photograph, which are made from radio waves that are coming from our nearby galaxy. And also there are now pictures of our own galaxy's black hole, taking the radio picture. So basically, in the universe, there are black holes which are due to the stars themselves and at the centers of galaxies. So these black holes at the centers of our galaxies are called supermassive black holes. And they formed, why did they form? Well, there are many theories about how they formed. They basically co-grew with the galaxies themselves. Some people think that at the early universe, the universe was more homogeneous. And then there are dark matter, there's a lot of dark matter. And then some of these dark matter may be collapsed. And then there are some gases that may also collapse together with the dark matter. And then they form some small black holes, the so-called seed black holes. And the seed black holes may either merge with each other, or they may accrete more gas on them, and then they grew into these kind of supermassive black holes. There are theories about how the black holes formed and how they grew, and this is really a task of astrophysics to study how they had evolved up till now. So these are observations, and then more, I think, in 2020, these three scientists were given the Nobel Prize about black holes. So Robert Penrose is a theoretical physicist who discussed mathematically the structures of geometry near black holes. And these two scientists are observers who did the observation of the stars around the Milky Way black hole. So in particular, Andrea Ghez is a professor at UCLA, near us. And Reinhard Genzel, I think he's actually half-time at UC Berkeley and half-time at the Max Planck Institute. So both people are from California, I guess. We should be very proud. So apart from the black holes, the other the other thing that Einstein's theory of relativity deals with is this expansion of the universe. So in the math of his theory, the universe can be expanding or contracting but he kind of was too, he's like, oh, why can the universe be changing in time? So he was a little bit uneasy about it, but Edwin Hubble, who was an astronomer who worked in the area, okay, this is the telescope at Mount Wilson. I think he actually used this telescope or its former telescope to actually discover that galaxies, I think that there are discoveries of the galaxies which are outside the Milky Way galaxies, okay? So when you look at stars, you see the stars are mainly from the Milky Way galaxy. And then sometimes you see a little bit of blurb of things which are other galaxies which are outside of the Milky Way. And it's just those galaxies, you can only see the whole galaxy as a whole. You can't, for those little bit farther galaxies, you can't see the stars in them. You just see the whole thing as one thing, okay? And those galaxies turn out to be moving away from us. And it turns out the farther away the galaxies are, the faster they're moving away from us. Okay, that just means that the universe as a whole is expanding. So that's why the farther away they are, the farther they're moving away. So Hubble discovered the expansion of the universe, and Einstein came and discussed with him. So this is a picture of Einstein and his wife at the Athenaeum at CalTech in 1931. And this is Mount Wilson seen from CalTech. So you see, we feel very connected to this discovery of the expansion of the universe. So I think this 1931 was a little bit before Einstein he moved full-time to the US. I think at that time the Nazis were persecuting the Jews already, and then very soon he moved to the US and moved to Princeton. So this expansion of the universe, I think right now we have a much better picture of, this is our understanding of how the universe came into being and how it kind of evolved. So the picture is that at the beginning it's very hot, and then as the universe expands, it cools down. It cools down. So when the thing expands, the particles move slower, it cools down, and then there was some moment when the universe was very uniform, and then somehow under gravity, structures, dense and underdense regions start forming, galaxies started forming, and then, okay, I guess here you have some galaxies, and then inside galaxies you have some stars, and then we're here. So the universe has had a history. And this is what we know right now. And then we have a lot of mysteries about the universe because a large fraction of the matter in the universe are called dark matter. It is because we don't exactly know what they are. And we only know that they serve the purpose of having gravity in the universe, but we don't know what other interactions that they have. And we also have the so-called dark energy, which is also very mysterious for us. So I think it just means that we have a lot of holes in our knowledge about the universe, but with that, we are able to understand, we're able to observe that the structure has formed over the past 13 billion years. So the final prediction is the gravitational waves. So these are basically the three kind of predictions. As I said, Newton's gravity is instant. Any two objects, there's a force between them, and that's it. But with Einstein's relativity, gravity is just a little bit like electromagnetic waves. You know, when you shake some electric charge, like in your phone, right? They drive some current, and the electromagnetic wave will move away, and you can communicate. With gravity, if you have some object shaking around, they emit gravitational waves. It's just that and the effect of the waves are very simple. If you have two objects that are separated, when a gravitational wave with amplitude h comes, it'll just change the distance, the relative distance of the two free objects by the distance times the amplitude of the wave. So it's a simple effect. It's just that it's very hard to generate an h because gravity is a very small effect. Think about it, the Earth is so heavy, and the only effect the Earth has is that things will fall on the surface. But think about your phone. It has just tiny little thing, and there's a lot of electrons moving around, and it can send current, you can communicate, a lot of things you can do. With gravity, your phone just falls, and that's it. So very little information you can encode under gravity. So it's very hard to generate. So the one example I use is to say, okay, if you have, so people even computed this. They say, if you're 1 meter away from the hydrogen bomb explosion, like this one, very lot of mass is moving, and then if you compute the h is 10 to the minus 27. So it basically, it means if you have 1 meter things, if you do this, the change is 10 to the minus 27 meters. So it's a very weak effect, very weak. So therefore, when people trying to measure gravitational waves, they are aiming at something generated in the deep universe, when things are moving around with a lot more energy than the hydrogen bomb, etc. Okay, so nevertheless, people started trying to measure these gravitational waves by building very sensitive devices. So the current way that we're using is the so-called laser interferometer. So it uses light to measure very small distances. So the idea is you shine some laser light. Light are oscillations, are waves, and the wavelength of light is 10 to the minus 7 meters. They're very tiny distance. If you change a little bit the distance, it changes the little bit of the waves here, and then the signal, there will be some different signal. So it'll be light is the best bet for measuring small changes in distance. Okay, so these are wavelengths, and then when your mirror moves, if these are mirrors, if you move a little bit of the mirror, it'll give you some signal light. And that's the principle for us to measure these gravitational waves. So the video here shows that it's the same kind of idea. You have this light, as the mirrors move tiny distances, it'll have different intensity here, and then you're able to measure the effect of gravitational waves. So the ingredients here are basically using light, which is very sensitive because wavelength is very short. And the other ingredient is that the distance separated between this one and that one is very long, because the gravitational wave changes the fractional distance. Okay, so therefore, if you have two things which are already separated, the additional change in distance is bigger. So therefore, the laser interferometers that are built to detect these gravitational waves are actually kilometer in scale, as I will show in the next page. Okay, so this is basically showing that the light, showing the light interfering to give you the signal. So here, this is a picture from the sky of one of the so-called laser interferometer gravitational wave observatory. So it is 4 kilometers in distance. So it's like 3 miles, 2.5 miles. It's pretty far. You have to drive a little bit from one end to the other end. So, and another site is in Louisiana. So the previous site is in Washington, and this is in Louisiana. And these two sites are basically these very sensitive devices for measuring these distances. And these devices are able to measure 10 to the minus 18 meters of relative distance change between these mirrors. And these mirrors are put in these tubes because you have to not have air in the light beams, so that the light beams travel in vacuum inside these vacuum tubes. And then you also isolate these mirrors from the ground motion by suspending them in this very delicate suspension system. And then you want to measure these 10 to the minus 18 meters. That's just because if you're able to measure these distances, you're able to reach collisions of black holes, which are, you have to reach a far enough volume in the universe so that there's frequent enough of such events taking place every year. So the frequency that we're able to measure is from 30 hertz to a few kilohertz. And that's just the band that your ear is sensitive to. So in some sense, these gravitational waves are basically black holes which are circling each other, and they stir the gravitational space-time geometry, and they shake everything. And then in principle, if your ear, of course, is not as sensitive, but the idea is that they are trying to move your ear at, they don't move at 10 to the minus 18 meters. If the things are separated by kilometer scale, they move this much. You can scale it down to your ear and calculate how much the ear will move, but that's not enough for you to hear it. But the principles are the same. The motions of these waves comes in, and they move these mirrors. So around 10 years ago, we had the first detection. So basically these detections, these are time, and this is the motion of those mirrors. So this is called strain, is the relative change in distance. And these are 10 to the minus 21 relative change in distance, which corresponds to 10 to the minus 18 meters change. And the idea is that these waves have small amplitude at the beginning, and then gradually, and these two black holes are getting closer, and then they have a higher frequency, and then they have a higher amplitude. So in this picture, it illustrates, in this video, it illustrates the waves we're detecting. So the idea is that this is like an embedding diagram of the curvature of space-time around the black holes. The color here is the rate of flow of time. Okay, so time is very slow around the black holes, and the black holes are curved. The space is curved around them, and these two black holes just circle around each other, and then they radiate these gravitational waves that will reach us. Okay, so around these black holes, the wave amplitude is very high. Space is distorted by a sizable fraction of itself. Okay, but then when it reaches the Earth, it's 10 to the minus 21 change in distance. So basically, these are the waves that we see. So from analyzing these waves, we can tell that these are two guys which are going around each other in this particular way. And then we can also see that at the final part, you have a final black hole that settles down to its final state. And therefore, we are able to extract information about such a collision process from these waves. And so because of this, the three founders of the LIGO project was awarded the Nobel Prize in 2017. So right now, in the past already 10 years, almost 10 years, where we have detected a lot more of these merging black holes. And therefore, we're getting a lot more details about how the geometry of space-time works around the black holes. And then we're trying to test these predictions of general relativity. So for example, the early part of the wave is about the two black holes circling each other, and the final part of the wave is some remnant waves that travel around the final black hole and then leaking out to us. So therefore, if the black hole's horizon is not completely black, then we'll be able to have some additional waves that are going to be coming out from this region, and then that will be a signature of new effects around black holes. And then the other thing is that right now we're able to measure, so that our distance of reach is only up till here in the recent universe. For black holes that formed during this time, the black holes emerging during this time, when they reach us, the waves are very weak. But in the future, we will be building new detectors that will be reaching to the early universe. And therefore, with gravitational wave observations, we are studying the predictions of relativity, the waves themselves, the black holes, and also the expansion of the universe. So that's what we're trying to do. So finally, let me also say that gravitational waves can also probe not only these black holes, which are empty space because all the masses are already squeezed beyond the horizon. So gravitational waves can also probe the so-called neutron star collision. So neutron stars are those stars that form from less heavy stars. So the most heavy stars, after they burn out their nuclear material, they go through an explosion, they form a black hole. The less heavy stars form neutron stars, and the even less heavy stars form the white dwarf stars. So these neutron stars are basically mostly made of neutrons. And these are very compact stars, and they can also circle each other and emit gravitational waves. So around the year 2017, we were able to discover a neutron star merger. So basically there was the gamma ray telescope that first discovered the gamma ray burst, and then gravitational wave detectors are able to localize the source, and then electromagnetic observations were able to see this particular event showing up in here. Before there was no event, and then there was this dot, which shows that there's this new explosion that goes on. And from this explosion, the idea is that from the explosion signal, we're able to discover signatures of elements forming. Okay, so I think this is a little bit about where the elements in the universe are coming from. So if you look at this table which shows the stable elements in terms of their number of protons and neutrons, what you find out is that for low elements, neutron and proton number are almost the same. But for heavier and heavier and heavier elements, they contain more neutrons than protons. And this is because protons have all positive charges and they repel each other, and that's not very stable for big nuclei. It's a little bit part of chemistry. So then the question is, how did these elements form? If you just take these elements and combine them, you tend to go along this line. And therefore, where did the elements that contain more neutrons come from in the universe? And these heavy elements include like gold and platinum and all the very expensive elements. So the idea is, for example, the gold. So the idea is that from the explosion of the universe, you can only form these kind of elements. And from the nuclear reactions in the stars, you can find these elements. But for the gold, for example, that have so many neutrons and very little protons, it's very hard to form them anywhere. And of course, you have the gold mines. As we are in the golden state, we dig the gold mines. But where did they come from? So one theory says that the gold came from the neutron stars, came from the mergers of neutron stars. Okay, so the process is the following. The stars, first they burn out their nuclear material and they become some kind of iron core, and they go through some kind of explosion, and after the explosion they will form these neutron stars. And then when you have the neutron stars, they have a lot of neutrons. They only have neutrons. And then you have these binary neutron stars in the universe. After the neutron stars merge, during the process when they merge, they will shed some of their materials as free neutrons in the vicinity. And there, because you have a lot of neutrons in this environment, they will undergo some kind of nuclear reaction, and then in this process, they can form the gold, or all of these other heavy elements. So in this diagram, which I stole somewhere, all of the purple elements are supposed to be formed through mainly merging neutron stars. So therefore, from observing these events where gravitational waves followed by that tiny dot, okay, where's the tiny dot? Followed by the tiny dot in here from your visible light. The reason why this dot is here is because of radiation. And that part of that radiation comes from the nuclear reactions that happen of those neutrons that are shed by these neutron stars. And these reactions, by analyzing the spectrum of this radiation, people can analyze what kind of nuclear reactions are going on, and underlying that one are the gold forming in this process. I think that's very amazing. Okay, so this is, I think I will just summarize my talk. So I think as I mentioned, this gravitational wave can be compared to ripples in space-time geometry, because gravity is a curvature of space-time, and gravitational waves are changes in this space-time geometry. And these gravitational waves that we observe, they serve two purposes. They first confirmed that gravity can propagate as waves, and it also, from the details of these waves, we can analyze the features of the black holes. And then the neutron star collisions, we're witnessing the heavy element production. And then, okay, so as I mentioned a little bit, right now the black holes we have seen are very close to us. They're from the close-by universe. And in the future, we would like to build more sensitive devices to measure black holes from more distant universe. And we want to measure more precise the gravitational waves more precisely, so that we look at the more finer details. And there are yet other predicted events which are more exotic than collisions of black holes that we hope we can discover. Okay, I will end my talk here. Thank you for listening.
Thank you so much, Dr. Chen. I know we have a FAFSA workshop that is happening later. I know there are a lot of seniors here. And do we have any questions for Dr. Chen that anyone might have at the moment? Okay, go ahead.
So when we try and measure gravitational waves, how do we know it's a gravitational wave and not anything else that could be interfering with us?
Yes, this is a very good question. So first of all, you try very hard to isolate your device from the ground motion and from the disturbances, other disturbances. And then you have a background level of noise. So normally when you see the signal's output, there's a certain level of fluctuations, and you can analyze the thermal physics, electronics, and ground motion. You can actually have a so-called noise budget. So you understand the background level of fluctuation, and then you suddenly see something going on. Okay, but then how do you know it's not a car or something? Or you monitor the environment. So you have to make sure when your signal comes, there's no unusual disturbances like a car or a person shaking or something. And finally, you have two detectors, which are separated by a few thousand kilometers. And then if they have corresponding signals, and then you are more confident that you have a true signal. So there are these ways.
Thank you.
I have two questions. My first one is, so if gravitational waves are ripples throughout space-time, does that mean that you can have different gravitational force in one area of space and is there like a base force based on Newtonian's sort of equation of gravitational force, and then it changes as the ripple goes through the universe? That's my first question. And my second question is based on Einstein's model of the universe expanding where it was hot and now it's cooling down and expanding. And you also mentioned that black holes, you're finding more of them merging. Is there a relationship between, like, what's the ultimate fate of the universe as far as, is it just going to end up being one very cold, still place eventually, or do black holes merging and emitting more energy somehow play a role in that? I hope these questions make sense.
Yes. So let me answer the first question. So gravitational waves can be understood as gravitational force, a distributed gravitational force field. So, but that is true if you have a smaller region in space, which is smaller than the size of the wavelength of the gravitational wave. You can think of the effect of the wave as just having a Newtonian gravitational potential being different and time dependent. And if you have a bigger region in space, qualitatively you still have a gravitational field which is space-time dependent, but the analogy to a Newtonian potential well is not as good anymore. But roughly speaking, you can understand gravitational wave as just, yes, gravity field is being changed at different locations. But normally the waves that we have change the gravitational potential very little, tiny little bit. It's a small perturbation. But if you're near the merging black holes where the gravitational wave is emitted, there the potential change due to the waves can be much bigger. So you can think of it that way.
Yeah, thank you.
The better analogy is that in electromagnetic fields, you have the Coulomb field, and then you have the electromagnetic wave. And the gravitational wave is more like an electromagnetic wave, but if you have an electromagnetic wave, when you have your antenna, the electromagnetic wave does exert electrostatic forces on the antenna, so you can use some electric potential to describe it. So the second question about the fate of the universe. I think there's something very weird about the recent universe, which is that it has been accelerating in this expansion. So normally, when you think of gravity, gravity is very attractive. So if you have things, the expansion of the universe was nothing but things are very hot and they try to fly apart from each other. So if you have gravity, they attract each other, so they gotta slow down. So therefore, up till the year 1990 or 1980, people thought the universe must slow down. And then they have a deceleration. And then they talk about measuring the deceleration parameter, which is how decelerating it is. But then the surprise came that the universe has been accelerating. And that led to the dark energy. And I think the reason why we have dark energy, it's like in psychology. If you have some kind of a pain and then you don't know what to do, you give a name to it, and then you feel peaceful. And then dark energy is almost something like that. You put something on the right-hand side of the equation to make it work, and you say, yes, this is dark energy. And every time you refer to this accelerated effect, you say, dark energy. But you don't have any other it's not clear what it really is, in the sense that other features of it is not known. The only role it has is it makes the universe accelerate in expansion. And that's pretty bad for the fate of the universe, because if we're accelerating in our expansion, temperature will go down, everything will go far apart, and then we will go to this death of heat death, or something people call the heat death. It's like it's very cold. And there's not really, and then people say that, if the universe becomes very cold, the black holes will all start evaporating, because right now the black holes, they do evaporate, but due to the Hawking radiation, but the ambient temperature of the universe is higher than the Hawking temperature. So all the black holes are actually getting bigger mass because the outside temperature is still high. But if the universe keeps expanding a factor of 1,000, 10,000, 10 to the 5, the universe gets colder and maybe all the black holes evaporate, and then that could be one fate, I think. But it could also be that the dark energy is not what we think it is. Maybe the expansion would not keep going, accelerating. That's not clear. So I think that's not very clear.
Thank you.
So we're calling matter, we don't know dark matter, and we're calling the energy, we don't know dark energy.
Something like that, I guess.
Okay, do we have more questions? So I think Dr.
Please,
Chen.
sorry, quick
Oh,
one.
yeah.
So LIGO has detected more than 100 gravitational waves for the last 10 years. Is there a difference between the gravitational waves created by the neutron stars, the black holes, or maybe two galaxies with black holes in the middle merging?
Right.
Is there a distinction, or
That's right. There are differences. So when they're far apart, they're just two things going around each other, and then the features are very similar. But the neutron stars, they are smaller in mass. They're lighter. The black holes are typically heavier. So for the lighter neutron stars, their waves progress less fast. They progress slowly. So they stay longer. The waveforms are longer in time, and they go around the same frequency for a long time before they merge. This is a neutron star. The black hole ones are shorter, and that's the early distinction. And then when the two black holes merge, they have one very distinctive way the black hole settles down. But the neutron stars, when they get close and disrupt each other, they may form a bigger neutron star and oscillate a little more, or there could be some different scenarios. So the end part of the wave will be different. And for the centers of the galaxy, those are very big black holes. And if they collide, they emit waves which are lower in frequency. And there are these new discoveries, which I didn't put in my talk, which uses signals from pulsars. And they detect very low frequency gravitational waves. And people recently discovered a noise background from this very heavy black holes emerging. And these waves have frequencies which are 10 to the minus 6 or 10 to the minus 7 hertz. That corresponds to one wave cycle per month, or one wave cycle per year, or a few weeks, that kind of thing. So those things are things going around each other much longer time. And those are the difference in the signal features. They are very different frequencies.
So the instruments you have in LIGO, they're just waiting to see the
Yeah.
moving, detecting gravitational waves? You're not pointing anything to the...
That's, yeah, you cannot point this one. The Earth is rotating, so therefore, at different time of the day and also the year, you have a different sensitivity to different locations. And there are different detectors in the world. There's 2 LIGOs, and there's a Virgo detector in Italy and a Kagra detector in Japan. And they all have different orientations. And therefore, when the wave comes, you sample a little different polarization, and you have different arrival time. So you have a little bit of angular pointing, but it's not so good. Yeah.
Are you going to be able to stick around a little bit more if
Sure.
there are more questions?
Yes.
Okay, I think we should give Dr. Chen a round of applause. There's still so much to study in the universe that we don't know. And please feel free to come and talk to him, ask him more questions. Like, I do want to let the people that need to go to the next thing, just take a breather. There's more. I'll make more hot water if you want to do a tea to go. I know some people like tea to go. And then there's snacks, okay? So thank you so much for being here. Thank you so much for coming. So thank you. Thank you for your